Good deal. Well, the other physics question on the topic of physics is, in the gym, it's force equals mass times acceleration, right? Isn't that
Yeah.
how it works? Isn't that
Yeah.
isn't that the
I don't
proper
want
formula?
to, yeah, I don't want to call people out, but this is a pet peeve of mine because you know what you're saying with F equals MA. That's not saying anything about how you lift the weight. F equals
Yeah, but
MA.
I'm massive and I'm
Yeah,
accelerating the
yeah,
bar,
yeah,
so
yeah.
that's my
But
force.
what is acceleration? The acceleration of gravity. So F equals mg, which is what? Weight. That means when there's 135 pounds on the bar, that's what F equals MA is, as F equals 135 pounds. Now, what this is just a personal pet peeve because the thought applies the same. You know, people say you got to apply more force to accelerate it. That's what people always say to build muscle. That's not what you're doing. Is power, which is force times velocity. And yes, the force remains the same because that's Newton's laws. You know, if there's 200 pounds on the bar, that's F. And so
Right.
that's the force. Now, how fast you move that force is your power, but you don't move a different force. You move the same force. It's 200 pounds. Just because you're moving it really fast doesn't make it 300 pounds or 100 pounds or anything different. It's, yeah. And that's,
Now I had freshman level physics, so I'm gonna see if I can stump you with this. I probably can't.
yeah.
So, what about on a deadlift when I'm applying a force with my feet into the ground? Does that change the formula, or is it still the same
No,
velocity?
you're applying, if you lift 500 pounds and you're able to move that 500 pounds, you are applying 500 pounds of force to the
Force.
earth. The earth is applying that back to you. Your hands are applying it to the bar. So the bar's F equals mg, which is 500 pounds. Your force is ma in the opposite direction, equal and opposite. And then how fast you move that would be the velocity, which would be the power generated. But you're moving F equals mg, which is 500 pounds no matter what.
But I'm moving it, but the force I'm applying is force equals MA.
Mg.
MA, isn't it?
Yeah,
My
which
feet
is
into the
mg.
ground, that originally is MA, and then as the bar starts to move, it's
But you're moving
velocity.
what? You're moving F, which is mg, which is gravity, which is 500 pounds.
Okay.
Yeah,
Well, I thought the actual before the bar moves, I thought the actual force I'm driving my feet into the ground.
yeah, you are. And then
Is
eventually
that
when
is
you
that
hit,
F equals MA?
yes, and
That's what I was
well,
saying.
that's your force. Yeah, and when it hits the F equals mg of 500 pounds, then they're equal and opposite. And that is when the bar will move. And then how fast you move it is the power generated in that
We have
process.
to talk about this on Table Talks.
you
You may have some
know, I
subscribers
like
drop off. We
there's
gotta
if I don't think there's a really brilliant physicist in the he used to be on the intense muscle. Oh my god, why? Oh, I feel so bad because he's an awesome dude. Big dude too. It was on intense muscle boards all the time. Nate, God, why? I'm so sorry, Nate. Geez, why is my after all this my brain? But he's a tenured physics professor. Brilliant dude. I tried to talk some physics ideas with him when I was like in grad school, uh, and he's smart. But I'm hesitant to talk about physics because there'll be someone out there who'll be like, well, technically there's higher ordered variances that because Newtonian physics is an approximation. It's an approximation that only works when gravity is constant, when there's no Taylor expansion past acceleration, past that second order derivative. There's better ways to do mechanics called like Lagrangian mechanics or Hamiltonian mechanics, which use energy. And then Lagrangian mechanics use like a first derivative, and then Hamiltonian mechanics use like the second order with related to momentum, and that's actually like what a Schrodinger equation would look like for quantum mechanics, like entry level quantum mechanics, and those are better methods. But like the F equals, and the other thing, like if you're taking physics, anyone listening to this, taking high school physics, college physics, all you are taking is F equals ma. That entire book is different ways to write F equals ma. F equals ma. So then you have so if you take, so A is F over m, right? And A is the second time derivative of position with respect to time. You integrate that once, and you get the integral up from that is velocity, and that's when you start getting the kinematic equations. And I have an old video on my YouTube of these, and you integrate again, and you get position, and then you get the kinematic equations involving position. You take A and make it an angular acceleration, and you get all the angular kinematic equations. You get 1/2 mv squared can be done from energy also, and that's equal PV equals nRT. So you take PV equals nRT in thermodynamics, and you have like volume, and pressure is force over area. So force over area times volume is force times length equals nRT, which is the same as basically energy, which is 1/2 mv squared. And they're all the same equation. So you need, that's why the professor in physics lets you bring an equation notebook into the exam, because everyone thinks they're all different things. They're all the same concept.
It's
They're
just
that Newton saw the apple fall and saw that acceleration of gravity was constant, and then realized that was a second derivative of position with respect to time. And even more wild, if I'm off on a tangent, since no one is listening right now, there's really no reason to have position in the kinematic equations whatsoever, because the only way you can tell a difference between position and velocity is in relation to something else. Because right now we're traveling at 34 kilometers per second. We are hauling ass through space, but we can't tell because the velocity is not like a change in anything. So really, I think the equations are totally screwed and makes physics hard, because we have two versions of the same thing, position and velocity. But position only differs from velocity if you're comparing it to something else. If you're not comparing it to something else, they're the exact same thing.